All right. There it goes. There we go. Okay. So here's another example I want to do, kind of like what we did last time. Very similar. We have A is 10, B is 0.25, as you can see. But just like before, we could figure out what R is. Since the B is positive and less than 1, R has to be in this form. And we could just solve for R. Namely, we just, it's just like the calculation on the first slide. We get R is 0.75. So that's what we get here, as you can see. So that's what we get here. But now let's do some calculations to make it more explicit, right? What we have here is x's, and this is our function, right? So here, I forgot to say this. Our decay rate, our R is 0.75. So what does this mean? This means the function values are decreasing by 75%. I mean, these are the function values in this table, as you can see. So here's our x values. Here's our function values. They're decreasing by 75%. In other words, for this one, let's say, from f of 0, you take 75% away of 10, you get this. If you find 75% of 2.5 and take it off, you get this. And so on and so forth. I mean, you can also see that this is not linear because the amount of change, as you can see, is not the same. Linear functions, the change is constant. That's what the slope is. Here, it's actually changing. And this is what I was trying to say before. If you take f of 1 and f of 0, and you calculate the relative change, you're going to get this. And this means f of 1, to get f of 1 from f of 0, you take 75% away from f of 0. In other words, the relative change is this, r. Well, negative r, I should say, because it's decreasing. Same thing with f of 1 and f of 2. Same thing with f of 3 and f of 4. If you take f of 3 and you, if you take f of 2, and you remove 75% of it and subtract it off, you get f of 3. And so on and so forth. Okay. Hopefully, I really hope that makes sense. That's what I'm trying to say here. Okay. Good. Now, this example, I think we might have done last time, but I really feel comfortable doing it again, mostly because I did it with the other class. But this also illustrates a case, or at least it alludes to it, where exponential functions appear in the sciences. If you are, I think chemists do this, I guess physicists do this also, but if you look at the concept of half-life, that's where, again, and that has to do with an element radioactively decaying, but it's going to radioactively decay by a percentage, as in the problem. So each day, for instance, you might lose a certain percentage of that. Well, if it's decreasing by 1%, what's happening? Exponential functions. I know exponential functions do come up in population growth. If you model the growth of a population, that's an exponential function. Although usually there are modifications you have to make because of resources, but that's a different story. Anyway, so here's an example. So we found this new element x. I don't know what it's called, but let's just call it element x. But somehow we found out if the element radioactively decays by 21% each day. Okay, by 21% each day. So the amount of it is decreasing. It's changing by a percentage exponential function. So again, what is this saying though? This is saying the amount you have, 21% of that will be gone. It'll take a day later. And then another day later, 21% of what's remaining will be gone, and so on and so forth. So let's suppose we have 200 milligrams of this. How much is going to be left after a week? In other words, how much will be left after 7 days? Well, let's get a formula first. Right? As you can see here, since it's decreasing by 21%, that tells us our R is 0.21. The initial amount I give you is 200 milligrams. But since it's decreasing, right, we're going to have 1 minus R. We're going to have 1 minus R, as you can see here. So again, we have our exponential function. We have the initial amount. We have 1 minus R. And we get this. So that's our exponential function. That's how much is left after X days. So after 7 days, 7 days, we're going to have this amount. I did check this calculation. It is correct. I think someone might have said it wasn't. I mean, whoever that is, they can email me. Or it might be in the other class. I don't remember. But I did double check this calculation. This is correct. Okay. But this is what we have here. So this is what we get. Okay. So this is what we have here. Now, so we get it less. But now the question is, how much are we going to have after 14 days? Well, instead of 7 then, we're going to have 14 as our X, and this is what we get. So again, here I replace X by 7. Here I replace X by 14. 14 days, this is what we get. And I should say this also, with exponential functions, you're never going to get 0 as an output. You just don't get 0 as an output. You don't get 0 as an output. I think I said that 3 times already. So it gets very close to 0, but you never actually get there. For instance, here's another part of it. Let's suppose we have, let's say we want to know how much is left after 30 days. So how much will be left after 30 days? Well, what do? We're going to replace X here by 30. As you can see, we're going to replace X by 30, okay? And then we just calculate, and we get this, which is pretty small. I think actually if you take X big enough, the output would be so small, your calculator will give you back 0, but it's really not 0. It's really rounding it to 0. So, you know, just something I thought I'd point out. So hopefully this example wasn't too bad. Let me just, let me see. Okay, so why don't we do another one then? So here's another one. So now we have another element called element Y. Now, for some reason, element Y, okay, is radioactively decaying by 50% each day. In other words, as each day goes by, 50% of the item breaks down. 50% of it. So again, it's a percent. What does that tell you? Exponential function. All right. So we're going to come up with a formula for this. This is actually almost identical to half-life. Half-life is actually how long it takes for 50% of the item to break down. So I guess this is actually an example of half-life. So here, let's suppose we have 1,000 milligrams of element Y. We're going to find out how much is there after X days. In other words, we're going to find a formula for the amount of element Y left over. Well, we have our R, right? Well, we have our initial condition, 1,000 milligrams. Our R is 0.5. And since it's decreasing, we're going to have, the amount is decreasing, we have decay. We're going to have this, minus. And so we get this. And that's what we get here. That's our formula. Okay? Now the question is, how much will be left after a week? Well, we got a formula, so for a week, you would replace x by 7. Okay, so that's good. So we're going to replace x by 7, and what do we get? We get this. So it's breaking down pretty good. Okay. All right, so that's good. Now here's another question. Look at this one. This one's a little bit different. We want to know how much is left after 9 hours. Not 9 days, 9 hours. So here you're going to have to do some kind of conversion. Now I want everyone to try this on their own. Let me just pause the recording. So 9 hours. Let me just pause the recording. I mean, here's sort of a hint. There's 24 hours in a day.